Hi. In this video, we will talk about fatigue and how it causes failure in mechanical components. First, a brief history of fatigue. In the early ages of industrialization, when water wheels were the most advanced piece of machinery, the mechanical systems were slow and under low stress. Therefore, a static loading stress analysis with a large factor of safety would be sufficient to design a mechanical component that would operate as expected for a long time. With the emergence of steam engine-powered machinery and faster motions, things changed. The mechanical systems used were under larger, repetitive loads. Varying or repetitive stress is an important part of fatigue and its analysis. There would be cases in which the stress value would completely reverse from tension to compression in a mechanical component. The added complexity and utilities of the machinery resulted in faster motion and longer hours of operation, which consequently increased mechanical failures of the components of the mechanical systems. These failures, however, could not be explained using the static loading analysis used by engineers thus far. Puzzled engineers attributed the failures of the components to the material getting tired after long hours of operation and simply collapsing. Soon after, however, they realized that the material properties did not change at all in the failed materials. They soon realized that the gradual growth of cracks inside the material causes the failures in the components. They named this type of failure fatigue failure after the earlier belief that the materials were getting tired during the operation. Starting mid-1800, scientists and engineers started to study and articulate fatigue failure. They have come up with theories and methods to understand and avoid fatigue failure. Some of these learnings are still being used today. Historically, fatigue failure has caused the collapse of railroads, structures, power transmission systems, airplane fuselage, engines, and many more mechanical systems. Today, fatigue and its analysis remain one of the most important parts of mechanical engineering design. There is still research being conducted to understand fatigue failure better and introduce methods to avoid it in mechanical systems. Probably the most typical example of systems that can experience fatigue is rotatory power transmission systems, which are widely used in automobiles, airplanes, power plants, robotics, and many more industries. Shafts, gears, and bearings are some of the typical components used in power transmission systems. Due to the rotatory nature of these systems, the stress value at some points in the mechanical parts varies drastically in each cycle. For example, the bending stress in the shaft reverses from tension to compression after half a turn rotation at one specific point. This alternating stress makes the shaft vulnerable to fatigue. So the design engineer must take fatigue into consideration. Generally, we can say fatigue must be considered if a component operates for a long duration and undergoes varying stress. Typically, such systems will go through hundreds of cycles per minute. Now, let's look at fatigue in more detail and understand the mechanism of fatigue failure. To understand fatigue failure better, let's quickly review the static load failure of a ductile material. A tensile test is used to obtain material characteristics and strengths. The material is loaded in tension with a slowly increasing force. After the yield strength of the material is reached, the material starts to experience plastic deformation. The specimen stretches and the cross-sections area reduces in a phenomenon known as necking. By continuing to apply the force, the material fractures. Fatigue failure differs from static load failure. Generally, fatigue failure occurs in 3 stages. The first stage is the initiation of microcrack in the material. The microcracks initiate at locations in the material with repeated locally high stress. These locations are often at a geometrical discontinuity at the surface of the material, such as keyways, grooves, and holes, material discontinuities such as voids, and manufacturing imperfections such as scratches. The second stage is the propagation of the microcrack to a macrocrack. This crack continues to grow at this stage as the repeated load continues. At the last stage, the macrocrack is large enough that the remaining material is insufficient to carry the load, and fails, similar to a static load failure of a brittle or ductile material. Now we look at these three stages of fatigue failure in more detail and with visualization. Let's imagine a simple bar made from a ductile material such as steel. Assume that we are applying a cycling force at the two ends of this bar. These forces cause cycling stresses in the material. Let's magnify a small section of the part to see the cracks better. We draw the free surfaces of the material and the grains that form this section. Nucleation of cracks starts in the presence of localized plastic strain at discontinuities. Geometrical discontinuities are usually at the surface of the material, so typically crack nucleation starts from the free surface in a single grain. Plastic strain due to the cycling loads breaks some atomic bonds, forming slip planes that pass one another. The slip planes move within a grain of the material in a direction requiring the least energy, which is the direction of maximum shear stress in a ductile material. In our example, the slip planes will have a direction with a 45-degree angle with the direction of the load. Continuing the load cycling, the slip planes would grow to a microcrack and eventually propagate into the next grain. Note that some microcracks cannot pass the grain borders and do not propagate through the material. After its formation, the microcrack will gradually pass across several grains at a 45-degree angle. This would constitute the first stage of fatigue failure. At this stage, the crack is large enough to start to propagate in the normal direction to the force. With each force cycle, the crack grows at a very low rate, typically 1 nanometer per cycle. This growth in the crack is the second stage of fatigue failure. After hundreds of thousands of cycles, the remaining material is too little to endure the force, and the part simply breaks. And this is the last stage of fatigue failure. Years of research and experiments have shown the relationship between the stress applied to a material and its life. These studies have given us information on how fast the nucleation phase occurs, how much time it takes for the crack to grow, and when will be the final failure of the material. It has been shown that larger stress values decrease the time it takes for cracks to nucleate. It has also been shown that the life of a material decreases as the stress value increases. To show this, let's make a plot, with the x-axis as the number of cycles that the stress is applied, and the y-axis showing the magnitude of stress. This curve shows microcrack nucleation, or phase 1 in the fatigue failure mechanism. We can see that at higher stress values, the cracks form faster. It also shows that if the stress level is low enough, it is possible that a crack never nucleates. There is another curve in this plot, the curve of final failure. The space between these two curves is the crack growth region. At higher stress levels, a crack initiates quickly, and most of the fatigue life is growing a crack until we reach a final failure. On the other hand, at lower stress levels, it takes longer for the crack to form, but a shorter period for the crack to grow and cause a failure. Note that it is also possible that the microcrack would never grow enough at lower levels of stress to cause a failure. Just as an example, it might take a material 10,000 cycles to form a microcrack. It would take another 75,000 cycles or a total of 85,000 cycles for the material to fail at a stress level of 100 megapascals. A simplified version of the final failure curve of this plot for ferrous material is known as an SN diagram. This diagram is the main tool that is used by engineers to predict and avoid fatigue failure in the design parts. This curve is obtained by thousands of fatigue failure experiments for different types of steel alloys. Fatigue failure with less than 1,000 cycles is known as low cycle fatigue, which is considered quasi-static, so fatigue analysis might not be necessary. The range with more than 1,000 cycles is where fatigue analysis is essential. The curve, however, flattens at some point around 1 million cycles in this region. This means that fatigue failure will never occur below a specific stress level. This stress level is known as the endurance limit. We can divide the SN diagram into two general sections: finite life, which is before the 1 million cycles mark, and infinite life, which is after the 1 million cycles mark. Using this diagram and based on the application, engineers design a part for finite or infinite life operation. And this would conclude this introduction video to fatigue. I hope you enjoyed the content and learned new materials. Thanks for watching this video. Hit the like button and subscribe if you liked it. Please also leave a comment and share your opinion.